Hi everyone, I'm Alex Vanyo and I'm super excited to be here with all of you today in person to get a chance to talk about optimizing your app for the large screen. So, to start with, I want to briefly talk about the why. Why large screens? We've seen a growing popularity of using Android apps on larger form factors, both on devices like Chromebooks, as well as an entirely new type of device, foldables. And there are more devices on the way in the tablet and foldable categories. Starting with Android 12L and then building upon it in Android 13 and future releases, the platform is making it easier to multitask and interact with your app in ways beyond the traditional portrait orientation phone experience that we're all very familiar with. To help you along that path, we've released a new set of material guidelines to help you design great apps for different form factors, as well as quality guidelines for evaluating the level of support that your app provides for the large screen. Today I'm going to walk through those quality guidelines and explore the tools and techniques that are currently available to you on your journey on optimizing your app for larger screens. These quality guidelines also tie into updates that are coming for apps in the Google Play Store. In the coming months, we'll be updating our featuring and ranking logic in Play for large screen devices to prioritize high-quality apps and games. For apps that don't meet basic compatibility requirements, we'll be updating Current Alert for users on large screens to help set expectations for how apps will look and function post-install. Users will also be able to see ratings and reviews split by device type. For example, different review categories for tablets and foldables, Chrome OS, Wear, or Auto. So, the large screen quality guidelines define three main tiers of large screen support: Tier 3, Tier 2, and Tier 1. Tier 3, as you can see, is basic support, which means an app is ready for large screens. Tier 2 then is better support, with an app being generally optimized for larger screens. And finally, the open-ended Tier 1 is where the app has the best large screen support and is using the different form factors to their fullest advantage. As I go up and talk about each of these tiers in turn, I'd encourage you to think about where your app currently stands and what steps you can take to improve the user experience no matter what tier you currently fall into. So let's start with Tier 3. The first level of large screen support. What does it take for an app to be ready for large screens and meet the criteria for Tier 3? Tier 3 is all about apps behaving well across changing orientations, screen sizes, and input modes without putting restrictions on sizes or orientations. So as the user rotates or folds their device or resizes an applications in freeform multi-window mode on Chrome OS, an app at Tier 3 will be preserving the user's state and function properly even if the UI hasn't been fully optimized yet to take advantage of the extra screen real estate. Especially if your app is currently locked to an orientation or declares aspect ratio limits, getting to Tier 3 requires challenging the assumptions you might have had over how your app will be positioned and interacted with while it's open. As an example, Android 12L and 13 bring an improved taskbar for app switching. So that makes it really easy to drag apps into split-screen multi-window modes. So it's important to test your app in these scenarios and make sure it behaves well when your window is being resized. Using your app in multi-window mode alongside another also means that other apps can try to access shared resources like the camera or the microphone at the same time as a different app, so it's essential to add the correct logic in your app and not assume that you're the only app that can be open. In Android 12L and 13, if the display size is bigger than 600 dp and you lock your orientation to portrait, this will enter you into compatibility mode when the users rotate their device into landscape on these larger devices. If your app falls into this category and you haven't updated to unlock the portrait or aspect ratio limits, be sure to test the behavior of your app in this compatibility mode, as some of your assumptions you might have made regarding the app's aspect ratio or screen orientation might not be valid in this modality. And then even beyond Chromebooks, many tablets are now being used with an attached keyboard, mouse, and stylus as alternate input options. So a great app experience means supporting these input modes in addition to our more standard touchscreen input. For Tier 3 in particular, an app should provide basic support for these different input types so that they are at least functional. As we'll see later though, there's a lot more that can be done with these more advanced forms of input. One of the most directly applicable cases where assumptions are being challenged is camera behavior and how it interacts with the device orientation. So if you're in the compatibility mode, because you've locked your orientation to portrait in your camera app, and you're not handling configuration changes, your camera preview may look like this in compatibility mode. To understand why this is happening and how to fix it, we need to take a look at how the camera orientation works on Android and how to correctly handle different orientations and window sizes. We can first define a natural orientation as a reference point for the orientation users tend to naturally use a device. So, for example, this is likely landscape for a laptop with a webcam on top of it, and portrait for a phone. For a tablet, this could be either one of the two. So, starting from this definition, we can define two other concepts. The first is camera orientation, which is the angle between the camera sensor and the natural orientation of the device. This is likely dependent on how the camera is physically mounted on a device, and in the past, this has usually been along with the long side of the screen 90 degrees off from the natural orientation. But with a foldable device, when it can physically change how it's oriented in space, this assumption is no longer as valid. So for that reason, starting from API 32, this field is no longer static, and it can be dynamically retrieved from the camera characteristics object. The other concept is device rotation, which measures how much the device is physically rotated from its natural orientation. Since there's main 4 different orientations that the user is expected to hold the device in, we can consider angles that are multiples of 90 and get this information by multiplying the value returned by display.getRotation. So here we have a code snippet putting all these concepts together to compute the rotation required to transform the camera sensor output into the device's current orientation. The rotation might need to be clockwise or counterclockwise, depending on which side of the device the camera is on, whether it's facing with the screen or facing away from the screen. And then we compute the difference between the two different rotation concepts mentioned before, and then do a bit of math to make sure that we're always between 0 and 360 degrees for the rotation between the camera output and our screen display. However, just handling the orientation doesn't guarantee a correct camera preview either. So for example, in multi-window mode here, you may need to display a landscape-shaped camera output into a portrait-shaped window while the app is only occupying half of the screen. So in this case, you might need to crop the image or scale it in such a way to match the aspect ratio that you actually have to display. Otherwise, you might get this shrinked preview or otherwise distorted or stretched preview image. So correctly transforming the image in every scenario can be challenging. So there's a code lab here with a step-by-step guide based on the Camera 2 APIs to help you in this task. Or, if you don't need direct access to the camera APIs, then Camera X from Jetpack can be the right solution for you as it automatically does most of this work for you, transforming the preview for screen sizes, handling the camera lifecycle, and updating the viewfinder after configuration change, and also controlling the access in a multi-window environment like I mentioned before. Camera X releases are also continuously being tested on many different devices to ensure the best compatibility. So I think that's enough of camera-specific issues supporting configuration changes. And the other main issue that apps run into when they're trying to unlock themselves from portrait is either crashing or losing state when configuration changes happen. So the ultimate goal here is relatively straightforward. If the user is rotating the device or the app is being resized, it's extremely frustrating as a user if the state is being wiped away. This could be small pieces of state like information that's being partially entered in a form or the current scroll state of where the user is in the app. And you can even consider navigation, where the user is within your app's overall navigation hierarchy as one of these pieces of state that is really annoying as a user if they rotate their device and that gets wiped. So admittedly, actually achieving that goal is difficult, and difficult in the sense of this is why we have so many conversations about architecture, and there's architecture talks at this conference. And navigation plays a huge part in making that complicated. So I'll touch more on that later in Tier 2. But the good news is that there's a lot of different tools to use to help preserve the state, and that the ones that you want to use depend on which technology your app is using. So all of these are ultimately backed by the activity's saved instance state. And for directly storing information in your activity, fragment, or view, you want to hook into these directly, on save instance state, non-restore instance state. In a view model, that survives configuration changes by default, but you can also use a save state handle to persist through process death as well, which you got for free, kind of, with activity fragment and view. For activity fragment and view, if you're using on saved instance state, on restore instance state, that state is surviving both configuration changes as well as process death. And then over in Compose, remember Savable and the related Saver APIs provide an idiomatic way to save pieces of data in saved instance state without having to dive through subclassing and overriding these methods. It's a lot easier to store individual pieces of state in Compose. And then also, to make sure that all that's actually working, there are tools for testing the saving and restoring, and you can verify behavior through hooks provided by Activity Scenario, both in Views and in Compose through the Android Compose test rule that you can see there. And then also in Compose in particular, there's a state restoration tester, which I want to take a more detailed look at now. The state restoration tester wraps a Compose test rule, and this facilitates saving state and simulating its restoration. So any calls to remember savable inside the state restoration tester's setContent call will be saved and restored when emulate saved instance state restore is called. So as an example, this test is checking that the incrementing count here is being saved through restoration. If we replace the remember savable there with a normal remember, then when we emulated saved instance state restoration, the count would be reinitialized to 0 and that last check would fail. But because we're using remember savable, that is being persisted, which you can consider a similar case if you are rotating your device and that's causing an activity recreation or through process death. So this isn't an architecture talk, so I'm going to move on. But one last remark is that all these changes to get to tier 3, as we've defined it for large screens, aren't exactly large screen specific. Apps that handle different orientations and configuration changes well will be more accessible and perform better in a variety of scenarios like changing locales or font sizes. So if you haven't already, I'd encourage you to try out disabling orientation or aspect ratio locks and see what steps you can take towards a tier 3 app. So once an app is meeting tier 3, where it's using all the screen space available to it while saving the user state, let's talk about the next step forward, which is moving towards tier 2. So an app meeting tier 2 has now optimized its UI. So it's taking full advantage of the screen space through alternate layouts or showing more content that might have been hidden away previously in menus or subscreens when there's less space available. So here, tier 3 has really set the foundation. Logic and state is in a nice place that makes it easier to optimize the UI to get to tier 2. So I keep mentioning the screen space actually available to the app, so I should probably define what I mean by that. The preferred way to determine the screen space available to your app is via the current window metrics, as returned by the window metrics calculator that's provided by the Jetpack WindowManager library. The compute current window metrics call returns the most relevant size for your application, since it's returning the value corresponding to the entire area available to your app based on the current windowing state. So the main idea here is that the physical size of the display isn't super relevant for what makes sense to show the user at any given point in time. If I'm on a really large tablet, but my app is in multi-window mode, then it doesn't really matter how big the tablet screen is. What's really relevant is the space that's available to my app as given to me by the user who's controlling the multi-window environment. So there's compute maximum window metrics there, and there are other display APIs, of course, that still exist and might be relevant in special situations, but I want to focus on that core idea of displaying content based on the screen size that's currently available to your app. So now that we've defined the size of the window, we need to deal with those arbitrary dimensions in a reasonable way. So to do this, we've partitioned the possible window sizes into window size classes, and then these are both grouped by width and height. So here I'm showing the width ones in particular, as we think those are the most relevant values for most apps, because most apps have vertically scrolling content, and the width is really what determines how much space is available. So these breakpoints partition common device types and also give them names, which is very important for a common language when going between design and implementation. So here, compact, compact width window size class corresponds to almost all phones in portrait mode, and that specifically is when there's a window width of less than 600 dp. A medium window width is then between 600 dp and 840 dp, which corresponds to tablets in portrait mode and the inner displays of foldables in portrait mode. And then finally, the expanded width is everything at 840 dp or more, which is landscape for tablets, landscape for inner displays of foldables, and desktop devices like Chromebooks. So one important note here is that these classify specific device types when apps are in full screen, but I do want to highlight that there's a difference between the maximum size window size class that could be supported on a device and the current window size class available again. So an app that's in a freeform resizable window on a Chromebook might be switching between all three of these device types as the user is resizing the window bigger and smaller. So for Compose specifically, the Material 3 window size class library packages both of these concepts together and takes care of most of these steps and is built upon the Jetpack WindowManager APIs. And so with the calculate window size class call, passing it activity, then you get, as state, the value of what the current window size class is. And the real power of this for Compose is that this is now just like any other ordinary state that you can then apply animations to, you can hoist state, and you can reuse logic based upon this now kind of materialized value of how much space is currently available to your app that you can make layout and design decisions for based on the window size classes. Now, if your app is currently using multiple activities and you aren't yet ready to make the migration in Compose, activity embedding is a way option as a stopgap to display multiple activities from the same app side by side if space allows. So the minimum space here is configurable via the Jetpack WindowManager library, and then behavior will gracefully degrade on API levels 31 and below where it isn't guaranteed to be supported. So if you're using fragments or Compose where you do have more control over your navigation structure and how different parts of your app interact, I want to talk about how best to think about the intersection between your primary navigation and the window size available. So the solution that makes it easiest to preserve the user state while still being flexible enough to show different content, depending on the screen size, is keeping your primary navigation structure fixed and independent of the screen size. So then, at each destination, you might display different content based on the window's screen size available using that state like I mentioned before in Compose. So to explore that in more detail, I'm going to take a look at an alternative, which is based on kind of this notion of a Boolean is tablet. So an idea would be to try to look and determine whether your current situation is phone or is tablet. Good luck defining that directly with foldables. And then having different navigation structures, one for phone and one for tablet. So the main issue here is that there isn't going to be a static answer. On a foldable device, an app might be displayed on the inner screen, and then when they fold it, it'll be displayed on the outer screen, and you might switch between which navigation you're trying to display at any given point. And same thing in a desktop environment, a free or resizable app might have that exact same issue. So as a result, in order to preserve the user state to meet tier 3, you'll end up needing to connect these two graphs and try to map all the state back and forth between your navigation structure. This is certainly possible, but you'll likely run into cases where you're trying to do some sort of navigation as a side effect of some screen size changing, and trying to keep all of this in sync together as you switch back and forth is much more painful than that first diagram. So you can keep the main spine of your navigation the same, and then within those each destinations, use the size of the screen as an input to vary what is being displayed at each destination, combining that with the other state in your app. One note here is that you do not have to have your main spine of your navigation handle all the navigation as the user might see it. So for example, if you're having a list detail at one of these destinations where you have multiple panes of content, if the space allows, you might have nested navigation within the destination itself, which is handled separately from this main static navigation structure in your app. There's nothing wrong with that. That's a much better way to think about this, and also allows you to have more direct control over that navigation as the user is folding, unfolding, resizing, where you might be displaying both panes of content, or you might only be displaying one. So that was a lot. So putting that all together, Tier 3 laid the groundwork to preserve the user state, and then by taking the window size into account for optimizing your app's UI based on the screen size, apps can reach Tier 2 to create layouts that can take advantage of the different screen space currently available to them, and then also update when that changes. So here's a few resources related to this topic and more information to explore further. So this now gets us to Tier 1. And so an app reaching into Tier 1 is creating a differentiated experience for itself based on the device and the input methods available to it. So this is an open-ended tier. It's the final tier. And the use cases here will probably vary depending on exactly what your app does. So for example, media apps might be more interested in posture support for foldable devices, whereas productivity apps will want to take full advantage of the different input methods and keyboard shortcuts or mouse and stylus inputs. One differentiating experience I want to highlight is adding support for drag and drop. So the APIs for enabling this have been around for a while, but a new Jetpack drag and drop library just went stable that makes it much easier to hook this into your app, both on the receiving side and on the sending side. So let's take a look at what that looks like. Drag Start Helper is a utility class that detects gestures commonly used to start a drag, such as long pressing or click and dragging with a mouse. You can set the visual look of what the dragged object looks like while it's being dragged by modifying the drag shadow object. Here we are using the default one. And then also note the global flag that allows for cross-app dragging. And since this is a content resource identifier and not just plain text, we need to use the drag flag global URI read to allow other apps to read from a content provider. Without it, other apps won't be receiving the drag events. Then, on the receiving side, the counterpart is the new drop helper, which is a utility class that takes care of listeners and drop targets. One thing to note here is the relationship between this and the edit text that might be contained. So there's an add inner edit text while building the drop helper to ensure proper drop target highlighting so that the edit text within the target may acquire focus rather than the target view itself. So these helpers are primarily focused on views, but built-in compose support is on the roadmap as well to make this easier there. On foldable devices, apps can observe the state of folding features via Jetpack WindowManager and adapt the UI based on how the device is physically positioned and folded. So, like I mentioned before, a media app can move the playing video to the vertical portion of the device perpendicular to the table, while playback controls and other information are down below. Another type of an experience that an app can really differentiate itself with is multi-instance. So an app you can think of like Chrome, where there might be multiple windows open that the user can be switching between, or if you have profiles, perhaps supporting having logged into multiple profiles at the same time, and then having different windows for each login profile. And then finally, productivity apps or creative apps might optimize for all the different peripherals and other forms of inputs that are available and provide rich keyboard, mouse, and stylus experiences that expose a lot more functionality and tools to power users via shortcuts or contextual menus that might be hidden away on smaller screens or devices when those inputs, those peripherals are not plugged in. So really the possibilities here are just unfolding. These are just a few of the ways that an app can set up itself apart on larger screens, but we know there are great ways out there that we haven't even thought of yet. The diversity of devices and inputs allow for apps to provide really engaging and useful experiences that I'm looking forward to seeing. So as a final summary, I hope this has been a helpful framework for you as you look at optimizing your app for larger screens and how different tools, libraries, and concepts fit into that process. A user's device is their unique personal portal into the digital world, and I think we have the responsibility and opportunity to provide a great experience however they're choosing to interact with our apps. Looks like I went pretty fast, so that's all I have. If anyone has any questions, I'd love to hear them, or you can meet and reach out to me afterwards. Thank you.